practical number 2, example number 1. For any integers a, b, c, if a divides b plus c and a divides b minus c, then we want to show here a divides 50b minus 22c. Now if given a divides b plus c, so this implies b plus c is multiple of a, so say it is ak1 for some integer k1 belongs to z. So this is equation number 1. Similarly, given a divides b minus c, so this implies b minus c is multiple of a, say a times k2 for some integer k2 belongs to z. Say this is equation number 2. Now we want to show that this 50b minus 20c is multiple of a. So from, if you add 1 plus 2, we get b plus c plus b minus c is equal to ak1 plus a times k2. Now if you simplify this cc will get cancelled here, and twice b is equal to a times k1 plus k2. Say this b is equal to a times k1 plus k2 plus 3, or you can, for k1 k2 you can write k3. Say this is k3, a times k3 divided by 2, where k3 is an integer and k3 is equal to k1 plus k2. Similarly, if you 1 minus 2, then we get b plus c minus b plus c. If you add these two equation, if you add 1 minus 2, then b minus c is equal to ak1 minus ak2. So this will be equal to, this bb will get cancelled here, and twice c is equal to a times k1 minus k2. So this implies, say k1 minus k2 is equal to, say twice c is equal to a k4, where k4 is an integer and k4 is equal to k1 plus k2, k1 minus k2, k1 minus k2. Then this implies c is equal to a k4 divided by 2. Now, so this is the value of b and c. Now I want to show that this 50b minus twice c is divisible by a. So that is, we want to show that it is multiple of a. So consider 50b minus 22c. So this is equal to, now put the value of b. So what is the value of b? It is equal to ak3 by 2. So this is equal to 50 ak3 divided by 2 minus 22 ak4 divided by 2. So from this, if you simplify this, if you divide by this 250, you will get 25, and if you divide 22 by 2, we get 11. So 25 ak3 minus 11 ak4. Now from this we can take a outside, and inside the bracket 25 k3 minus 11 k4. Now since k3 is an integer, k4 is an integer, now since 25 k3 11 k4 they are all integers, this implies 25 k3 minus 11 k4 is also an integer. So this implies put say write this into some this is an explanation. So this will be, for this term we can write this is equal to, we can write 50b minus 22c is equal to a times k5, where k5 is equal to 25k3 minus 11k4, which is an integer, so this implies this term is multiple of a, and hence a divides 50b minus 22c, hence the proof. Now next, example number 2, show that any integer, show that any integers, you can write here, show that any integer of the form any integer of the form 6k plus 5 can be written as 3k plus 2, but not conversely, thrice k plus 2 but not conversely. Converse is not true. So this is what we want to show here. Now take one particular example, particular case. Say here I am writing, suppose if you take any integer of the form 6k plus 5. So 6k plus 5 we can write, say if you take k is equal to 2, say k is equal to 2, then 6k plus 5 is 6k plus 5, if you take 17 can be written as 6 times 2 plus 5, and this 17 also can be written as 3 into 5 plus 2. So any integer which can be written as 6 times k plus 5, this is the value of k, and here this is the value of k, can be written as thrice k plus 2. This is what we want to show here. So now we are going to write here proof. See here proof. Now this given integer 6k plus 5, which can be written as thrice k, inside the bracket, say we can write this 6k as 3 times twice k, and 5 can be written as 3 plus 2. So from these two term, if you take 3 outside, we get twice k plus 1 plus 2. Now twice k is an integer, so put, say k, capital K is equal to twice k plus 1, so which is an integer. So this implies this 6k plus 5 can be written as 3 times capital K plus 2, where k is equal to twice k plus 1. Now we want to show that converse is not true, but so hence the proof. Now we want to show that converse is not true. That is, an integer, not every integer, of the form, say thrice k plus 2, cannot be expressed as 6k plus 5. So now say this, take k is equal to, take for case or even integer, say even integer. So let say k is equal to, say k is equal to 2i, for some I is an integer, and even integer can be written as in the form of twice I. So the thrice k plus 2 can be written as 3 times twice I plus 2, so which is equal to 6i plus 2. So an even integer can be expressed, even integer which is of the form thrice k plus 2 can be expressed as a 6i plus 2, not 6k plus 5. Hence the proof. Or you can take one example, particular example here, say if you take simple example, if we know that the 5 can be written as 3 into 1 plus 2, but 5 cannot be written as 6 into 1, 6 into something, 5 will written as 5, we can write the 5, sorry, not 5, even integer we should write, say 8 can be written as 3 into 2 plus 2, but 8 cannot be written as 6 times k plus 5, because if you take this equation has no solution, okay, and hence the proof. Now next, example number 3. Use division algorithm to establish every odd integers is neither example number 3. Every using division algorithm, what we want to show here, use division algorithm to show that or to establish that every odd integer is either of the form, every odd integer is of the form 4k plus 1 or 4k plus 3. So here we can take odd integer, say here 5 can be written as 4 times 1 plus 1, and if we take 7 can be written as 4 into 3, 4 into 1 plus 3. So every odd integers can be written as in this form, that we want to show here, and for that we want to use here division algorithm. Now we want to apply the division algorithm, so let us apply division algorithm. So we want to change the color. So apply the division algorithm on say integer 4 and n and 4. So if you divide n by 4, then n is equal to 4q plus r, where 0 less than or equal to r less than 4. So now since given n is a odd integers, given n is in odd integer, hence this implies n can be written as a twice m plus 1 for some integers. So if you put this value in this equation, we get twice m plus 1 is equal to 4q plus r. So this implies twice m is equal to 4q plus r minus 1. Now here the r has 4 cases where r is 0 less than or equal to r less than 4. So case 1, if r is equal to 0, then this implies twice m is equal to 4q minus 1, and this implies m is equal to 4q minus 1 divided by 2, which is not possible, since you can see here m is an integer. So since m is an integer, therefore this case is not possible. So case number 2, if r is 1, then twice m is equal to 4q plus 1 minus 1. In this equation here, put r is 1, so this implies twice m is equal to 4q, and this implies m is equal to twice q. So if m is equal to twice q, implies n in this equation, since n is equal to twice m plus 1, this implies n can be written as 2 times twice q plus 1. So this implies n is equal to 4q plus 1, and hence an odd integers can be written in this form. So now next, the case number 3. If r is equal to 2, then if you put r equal to 2 in this equation, we get twice m. This implies twice m is equal to 4q plus 2 minus 1. So this implies twice m is equal to 4q plus 1, and this implies m is equal to 4q plus 1 divided by 2, again, which is not possible. Why? Because m is an integer. This implies which is not possible, since m is an integer, and given this is not an integer, so this case is not possible. Case number 4, if r is equal to 3, then twice m is equal to 4q plus 3 minus 1. So this implies twice m is equal to 4q plus 2. So this implies m is equal to twice q plus 1. So put this value of m in the original equation of n. So what is the value of n here? N is equal to twice m plus 1. So n is equal to, since n is equal to twice m plus 1, this implies 2 times twice q plus 1 plus 1. So n is equal to 4q plus 3. So every integer can be written either 4q odd integer. What is n? N is an odd integer. We assume what is n? N is an odd integer. So every odd integer can be written as a 4q plus 1 or 4q plus 3. Example number next example, prove that. Next number, say D. Prove that no integer in the sequence is a perfect square. No integer in the sequence 1 1 1 1 1 1 1 1 1, that is 11 111 1111 11111, not a perfect square. No perfect square in this sequence is a perfect square. Is a perfect square. Is a perfect square. So we know that 9 is a perfect square because 9 can be written as 3 square. 16 is a perfect square, so which can be written as 4 square. But we want to show that this sequence is not a perfect square. So now again to change the color. Now consider, now we can write 11 is equal to 4 times 2 plus 3. 111 can be written as 4 times if we divide 1 1 1 by 4 1 1 by 4 sorry 4, then can be 27 plus 3. So every integer in this sequence, this 1 1 1 1 also can be written as 4 times something plus 3. So every integer in the sequence, given sequence, can be written as sequence 111 111 11,111 can be written as 4k plus 3 for some integer k. So say here k is 2. In this equation k is 2, here k is 27, like this. So now I want to show that any square of any integer, now we know that square of any integer is of the form 4k or 4k plus 1. That is say if a is even, say if a is even integer, then a is equal to twice q, say for some integer q. So what is a square is equal to 4q square, so which can be written as a square is equal to 4k. And if a is odd, then a is equal to twice q plus 1, and here if you square a square, then a square is equal to twice q plus 1 bracket square, which is equal to 4q square plus 4q plus 1. So this can be written as 4 times q square plus q plus 1, and hence which can be written as 4k k plus 1. So this implies square of any integer is of the form is of the form 4k or 4k plus 1, not 4k plus 3, and hence this implies, but every integer in this sequence can be written as 4k plus 3 for some integer 4k plus 3. So this implies in the given sequence 11, not this in the given sequence, not given sequence is no integer in the sequence, no integer is a perfect square, Now the last, we want to find first find the GCD of 56 and 72, and we want to express that GCD as a linear combination. So this is very simple, 56 and 72. So I am writing here, say example number 5. First step, find GCD of 56 and 72, and write GCD of 56 and 72 as 56x plus 72y. So this, first of all, apply the division algorithm here. So if you divide 72 by 56, then the quotient is 1 and remainder is 16. Next, if we divide 56 by 16, then the quotient is 3 and remainder is 8. Next, if we divide 16 by 8, then it is equal to 2, the remainder is 0. So at here we get remainder is 0. So the GCD of 56 and 72 is equal to 8. Now I want to express this 8 as linear combination. So step 2, first of all, this 8 can be written as 8 is equal to 56 into 1 minus 16 into 3. So this 8 can be written as 56 minus 16 into 3. Next, put the next remainder 16. So 56 into 1 minus the next remainder is 72 into 1 minus 72 into 1 minus 56 into 1 into 3. So this can be written as 56 into 1 minus 72 into 1 plus 56 into 3. So this is equal to 56. This is 1 times and this is 3 times. So total they are 4 times minus 72 into 1 times. So we write 8 is equal to, therefore 8 is equal to 56 times 4 plus 72 times 72 times 3, 72 times not 3 here, so 3. So this is 72 times 3, so 72 times 3, and here also minus 3, 72 times minus 3. So if you compare this equation with 8 is equal to 56 or x plus 72y, this implies x is equal to 4 and y is equal to minus 3. So this answer here, answer the GCD of 56 and 72 is equal to 8, and which can be written as 56 in 56x plus 72y, where x is equal to 4 and y is equal to minus 3. Now similarly you can solve this example. Say GCD of 24 and 138. Sorry. Second example. GCD of 24 and 138. Express this as 24x plus 138y. So again, now here divide the largest element by smallest element. So this is will be equal to 5 plus 18. Now divide this 24 by 18. The quotient will be 1, remainder will be 6, and now next time divide this 18 by 6, so the remainder will be 0. So the GCD, the last non-zero remainder is 6, and therefore GCD of 24 and 138 is equal to 6. Now want to express this GCD as a linear combination, so we start from 6, can be written as you can see here, this 6 can be written as 24 into 1, 24 into 1 minus 18 into 1. Next, this 24 into 1 minus 18 can be written as 138 minus 24 into 5 into 1. So this will be equal to 24 into 1 minus 138 into 1 minus 24 plus 24 into 1. So total 24 into this is 5 not 1, this is 5. So 24 total 6 minus 138 into 1. So if you simplify, this is 24 into 6 minus 132, 138. So this will be equal to, so hence GCD of 24 and 138 is equal to 6, which can be written as 24 into x plus 138 into y, where x is equal to 6 x is equal to 6, correct, and y is equal to minus 1. The next example, this 119 and 272, you can try it for, I am going to solve this. next example F, find LCM of 143227 of 143 and 227. Now we know that the LCM into GCD is multiplication of A into B, that is LCM is equal to A into B divided by GCD. So first we are going to find the GCD of, so step first, GCD of 143 and 227. Now divide smallest element by, so the step first, divide the largest element by smallest element into the quotient is 1, remainder is 84. Next 143, if we divide by 84, again quotient is 1, remainder is 59. And if we divide 84 by again 59, the quotient is 1, remainder is 25. And if we divide 59 by 25, quotient is 2, remainder is 9. And if we divide 25 by 9, then the quotient will be 2 and remainder is 7. Next, if we divide 9 by 7, then it will be equal to 1 plus 2, and if we divide 7 by 2, then this will be equal to 3 plus 1, and if we divide 2 by 1, we get 1 into 2 plus 0. So at this step we get 0, so this is our GCD. So this is the GCD. So the GCD is 1 here. This implies, now in the next step, since GCD is 1, this implies LCM is equal to 143 into 227 divided by 1. So to multiply 143 by 227, we get it is 32,000. LCM is equal to 32,461. The next example number, say the second example from example F, find the LCM of 306. Find the LCM of 306 and 657. Now this 657, we know that the GCD is equal, LCM is equal to A into B and divided by GCD of AB. So first we are going to find the GCD here. So step first, GCD of 306 and 657. So we divide 657 by 306. So this will be equal to so the quotient will be 2 and the remainder will be 45. Next, if we divide 306 by 45, quotient will be 6 and remainder will be 36. Next, if we divide 45 by 36, quotient will be 1 and remainder will be 9. And if we divide 36 by 9, this will be equal to 4 plus 0. So at this step we get 0. So this is the RGCD, and hence GCD is equal to 9. So what is LCM here? LCM is equal to 306 into 657 divided by GCD, which is 9. That is 306 divided by into 657 divided by 9. So if you divide 306 by 9, we get 34. So this will be equal to 34 into 656, and if you multiply 656 by 34, we get 22,304. So what is the answer here? The answer is LCM is equal to 22,304.